Now, in this video, we will going to discuss about the definitions of elastic constants. The first one is the modulus of elasticity or Young's modulus. So what is that? The modulus of elasticity is the constant of proportionality and is defined as the ratio of the linear stress by the linear strain or linear stress to linear strain within the elastic limit. It is denoted by E. So what is modulus of elasticity? E will be equal to the linear stress by linear strain, which is sigma by epsilon. So what is modulus of rigidity or shear modulus? Shear modulus is defined as the ratio of shear stress to shear strain within the elastic limit. So shear modulus or modulus of rigidity, which is C, will be equal to shear stress by shear strain, that is sigma tau by phi. So similarly, you are going to take as bulk modulus. So the ratio of change in volume to the original volume is known as the volumetric strain, which is epsilon V. And the ratio of direct stress to the volumetric strain or the corresponding volumetric strain is found to be constant, and it is given by it's for a given material when the deformation is within the elastic limit. So what is that? Bulk modulus will be equal to the ratio of volumetric strain, which is that is the direct stress by the volumetric strain, which is epsilon. Direct stress is sigma, and what is the volumetric strain, which is delta V by V, which is equal to sigma by epsilon V within the elastic limit. What is the Poisson's ratio? So the Poisson's ratio is defined as the ratio of lateral strain to the longitudinal strain is constant for a given material when the material is stressed within the elastic limit, and this ratio is called the Poisson's ratio, which has already been explained in our previous videos. So what is that Poisson's ratio? 1 by m will be equal to lateral strain by linear or longitudinal strain. So now we will going to have some relations between the elastic constants. What is the complementary shear and state of simple shear? So prove that a material subjected to pure shear in two perpendicular planes has diagonal tension and compression of the same magnitude at 45 degrees to the planes of shear forces. So what is that? When we are considering the figure A, what we have ABCD is subjected to a shear stress, which is tau xy along the plane of AD and tau xy in the direction towards the bottom side, which is on the plane BC. So now when you are considering this, figure A shows an infinitely small block of ABCD and the shear stress intensity tau xy. This shear tends to rotate the block in the clockwise direction as no other force is acting. Now the block is not in equilibrium condition. So that is what we say here. In the first block of ABCD, when the tau xy is applied only in one particular direction, so only on two faces, which is two parallel faces, this will try to tend to rotate in the clockwise direction. But now the body is not in equilibrium condition. So next, when it comes to attain the equilibrium condition, a couple has to be applied in counterclockwise direction. This can be achieved by having a shear stress intensity, which is tau by x on faces of AB and CD in the direction as shown in figure B. So that means when you are considering the figure B, so initially we have a shear stress which is applied between AD and BC. So it tends to rotate in clockwise direction. It is not in equilibrium condition. If you want to have an equilibrium condition, then you have to have a counterclockwise couple, which is tau by x is acting along the direction of AB and tau by x which is acting in the direction opposite to this. So now the body will be in equilibrium condition, which is as shown in figure B. Now consider the unit thickness. What is the moment of couple? The moment of couple will be equal to the force into lever arm. So what is that? Tau xy, which is tau xy into AD into 1, because infinitesimal unit thickness. So along the face AD into 1 into tau xy. So into then the perpendicular distance, which is AB. So that is this distance, which is AB, which will going to be so tau xy into AD into 1 into this distance, which is AB, which is the perpendicular distance. So that will be the moment of couple considering the unit thickness. So moment of balancing couple will be equal to, what is the balancing couple? The balancing couple will be equal to tau y x into AB into 1 into AD, that is the balancing couple. So because it is in the clockwise direction and this will be in the counterclockwise direction. So balancing couple will be equal to tau y x into AB into 1 into AD. So for the equilibrium condition, what is the meaning of that? So both should be having equal. So that means moment of couple and moment of balancing couple should be equal. So that means tau xy into AD into 1 into AB will be equal to tau yx into AB into 1 into AD. So as we know, AD will be both on the left hand side and the right hand side. Therefore, tau xy will be equal to tau yx. Therefore, the shear stress tau x is called the complementary shear stress. This theory states that a shear stress is given direction cannot exist without a balancing shear stress of equal intensity in the direction at right angles to it. So that means whenever you have applied any shear stress, to that there should be a corresponding shear stress but at the right angles to it. Then only it will going to be having that existence. That is the reason why we say the complementary shear stress. The complementary is nothing but it is at 90 degrees. So that means we have ABCD, tau xy is acting in this tau x AB, tau x is acting along the plane AB and tau xy is acting in the direction perpendicular to AB, that is on BC, which is tau xy. Similarly, when you have tau xy is acting along the direction of AD, tau yx will going to be acting in perpendicular to tau xy, which is CD, along the direction of CD into 1. So when you have at the right angle, so here if you are considering a plane of a square section of ABCD, so tau acting in this direction and also the complementary is tau is in this direction. Similarly, both will going to have this. The complementary shear, that will be sigma, will going to be acting in this direction. So if you are considering at the right angle triangle AB, BC and CA, so AB is tau is acting along the direction to the from right to left, from left to right, that is tau, and from BC it is acting downwards. So since these AB and BC are equal, so this will be angle at 45 degrees, then the stress, normal stress will going to be on the diagonal AC, which is sigma, which is as shown in figure E. So thus, if section is subjected to pure shear, the state of stress is in element at that section is shown in figure C. This state is known as simple shear. That means where in the simple shear, where you are not going to have any type of stress other than shear. So similarly, considering the figure D, take tau xy is equal to tau x which is equal to tau. So let AB is equal to BC, which is equal to CD, which is equal to DA, which is equal to A. That means it's a square section. The thickness of the block has been considered as unity. That is, it will be equal to 1. So what is the length of the diagonal? So length of the diagonal AC will be equal to BD, which is equal to root 2 into A. So by applying the Pythagoras theorem, what we are knowing here is if this is A and this is A, what is AC? AC is equal to square root of AB square plus BC square. AB square is nothing but A square plus BC square is A square again. A square plus A square will be equal to 2A square. So that is AC will be equal to square root of 2A square is equal to root 2 into root of A square, root 2 into A. So that is the reason why the length of the diagonal AC will be equal to root 2 into A. Consider a section along AC and let sigma be the stress in the direction, sigma be the stress on the section. Consider the equilibrium of the triangular portion which is ABC, which is as shown in the figure E. So that means we are referring about this particular figure, what we are talking about now. So in that, what he says here, resolving the forces perpendicular to the diagonal due to sig tau will be equal to tau into AB into 1 into cos 45 plus tau into BC into 1 into sine 45. Sorry, again, tau into BC into 1 into cos 45. So tau into AB is A into 1 into cos 45 plus tau into A into 1 into cos 45. That is equal to 2 into tau into A into 1 into cos 45. Therefore, what is cos 45? Root 2 into root 2. So that is A tau into root 2 into root 2 into tau into A into 1 by root 2. So that means I am expressing the 2 in terms of root 2 into root 2, which becomes 2 into tau into A into 1 into what is cos 45, 1 by root 2. So since I want to cancel that root 2 in the denominator, therefore that 2 can be written as root 2 into root 2. So when you multiply this, it is root of root 4, it is equal to 2 again. So once you cancel this root 2, so you're going to get it as root 2 into A into tau. So therefore, tensile stress induced in the diagonal AC will be equal to sigma, which is tensile force induced in the diagonal AC will be equal to sigma into AC into 1. You know root 2 into A into sigma. So what is AC? That is root 2 into A into sigma. That is AC. So for equilibrium, root 2 into A into sigma tau will be equal to root 2 into A into sigma. So therefore, cancels on both the sides, so tau will be equal to sigma. Hence, the resultant will be equal to 0. So this is how. Therefore, similarly, the intensity of compressive stress sigma in the plane BD is numerically equal to tau. Thus, a state of simple shear produces pure tensile or uncompressive stresses across the planes inclined at an angle of 45 degrees to those of pure shear, and intensities of these direct stresses are equal to the intensity of pure shear stress. So that is what we will going to get it in this. So here, so due to tau which will be on this, so here what we are interested is in the resolving the forces in the perpendicular direction what we are talking about. So here tau will be equal to tau into AC into AC into cos 45 and BC into again cos 45. So that is AC into cos 45. So that is what we were shown here. That is this value tau into AB into 1 into cos 45 and plus tau into BC into 1 into cos 45, which will be 2 tau. You're going to get it. So here, once you get that root 2, so root 2 into A into tau. So tensile stress induced in the diagonal AC. So what is that diagonal AC? Tensile stress which is equal to sigma. So tensile force induced, that is sigma is tensile force is for sigma into area of cross section. Sigma is stress into AC into 1, it is the cross section, which will be equal to what is AC? That is root 2 into 1, root 2 into A into sigma. So why that AC will be, you can express AC as root 2 into A, where I will going to get that answer. That answer we got it from here, which is AC is equal to root 2 into A. You substitute that value in this particular expression, that is root 2 into A into sigma. So for equilibrium, root 2 into A into sigma is equal to root 2 into A into tau. So that will be equal to tau is equal to sigma. So hence the resultant is 0. So this is how you will be able to get the derivation. So in the next video, we will going to consider about the other relationship of the elastic constants. Thank you very much.